Problem number 7 is the same type of problem as the tightrope walker we saw earlier. A person weighing 560 newtons is lying in a hammock that is fixed at both ends. The ropes of the hammock make angles of 45 degrees and 30 degrees with the horizontal. The question asks us to find the tension in the ropes for each direction. Since the hammock is in static equilibrium, the net force acting on it is zero. This means the net force in both the x-axis and the y-axis directions is zero. I will explain this problem using a more systematic method. First, to solve any problem in physics, we must decide on a coordinate system and an origin. Since this is motion on a plane, we'll set up a Cartesian coordinate system. Following standard directions, we'll define right as the positive x direction and up as the positive y direction. Usually, it's most convenient to set the origin at the object's location. Now let's draw a free body diagram for this equilibrium state. There are three forces acting on the hammock, two tensions acting diagonally to the right and left, and the force of gravity acting vertically downward. Let's start with the equilibrium in the horizontal direction. Because the object is in equilibrium, the sum of all horizontal forces, the vector sum considering both direction and magnitude, is zero. Now let's add up all the horizontal components of the three forces acting on the hammock. Since tension T1 is acting toward the upper left, its horizontal component is minus T1 times cosine 45 degrees. It is very important to realize that this value is negative. Based on our coordinate system, right is positive. Since T1 acts to the left, it takes a negative value. Using the same method, the horizontal component of tension T2 is T2 times cosine 30 degrees, and this takes a positive value. Finally, the horizontal component of the downward gravitational force is zero. Since the hammock is in static equilibrium, the sum of these three horizontal forces equals zero. Now this is our first equation. Next, let's look at the vertical equilibrium. Both tension T1 and T2 are acting upward, so we can find their magnitudes using sine functions, and both will have positive signs. The vertical component of gravity acts downward, so it has a negative value of 560 newtons. This is our second equation. If we set up the equations and solve the two relationships simultaneously, T1 is calculated as 400 newtons and T2 is 502 newtons. We've just solved a basic equilibrium problem using simple force decomposition. The key here is to accurately understand the positive and negative signs of the forces based on the coordinate system you've set. If you understand this principle, you can solve even the most complex systems step by step. That's it for today's lecture. Great job, everyone. I'll see you next time.